Carom is a very popular indoor game. Next time when you play it, combining your skills with concepts of two-dimensional collisions, you might be able to execute even the toughest of shots in Carom. Let's discuss this case in detail here. You must have surely enjoyed the fun and thrill of playing air hockey. Can you tell the type of collision that takes place between two hockey pucks? Well, it can be approximated to be an elastic collision in two dimensions. Let us study about such an elastic collision in two dimensions and also understand how conservation laws can be applied to it. We have already learned about one-dimensional or head-on collisions in which the colliding objects move along the same straight line before and after the collision. However, in a two-dimensional collision, after collision, the objects move at an angle to their original trajectory. To get a clearer picture, let us consider the case of elastic collision between two hockey pucks. Assume puck 1 has mass m1 and puck 2 has mass m2. While puck 2 is initially at rest, puck 1 moves along the positive x-axis with an initial velocity vector v1i. Both the pucks collide, and after the collision, puck 1 moves with a velocity vector v1f at an angle theta 1 with the x-axis, and puck 2 moves with a velocity vector v2f at an angle theta 2 with the x-axis. Now let us apply the conservation laws for such a collision. To begin with, since we are considering a two-dimensional motion, we need to resolve the velocities for their x and y component. The components of vector v1f along the x-axis is v1f cos theta 1, and that along y-axis is v1f sin theta 1. Similarly, the components of vector v2f along x-axis is v2f cos theta 2, and that along y-axis is v2f sin theta 2. Further, we know that in all collisions, the total linear momentum of the system is always conserved. That is, total momentum before collision is equal to the total momentum after the collision. Vector p1i plus vector p2i equals to vector p1f plus vector p2f. Here, one should note that as momentum is a vector quantity, its components in the x and y directions must also be conserved. Hence, the expression for conservation of momentum along the x-axis can be written as equation 2. Since v2i equals to 0, we can rewrite the equation as follows. Observe that before collision, velocity of the body was along the x-axis. Hence, its component along the y-axis is 0. Also, as the puck 2 was at rest, hence initial net momentum along y-axis was 0. The expression for conservation of momentum along y-axis can be written as 0 plus 0 equals m1 v1f sin theta 1 plus m2 v2f sin theta 2. Equation 3. Here, we need to recall that as the collision is an elastic one, total kinetic energy before the collision is equal to the total kinetic energy after the collision. Thus, K1I plus K2I equals to K1F plus K2F. Substituting the formula for kinetic energy of the pucks before and after the collision, we get the following equation. Now, as puck 2 is initially at rest, V2I equals to 0, and hence half M2 V2I square equals to 0. Thus, we get the following equation. Thus, we have seen how in a two-dimensional elastic collision, conservation laws can be applied. Looking at the equations 2, 3, and 4, we have 3 equations and 7 variables, that is, 2 masses, m1 and m2, 3 speeds, v1i, v1f, and v2f, and 2 angles, theta 1 and theta 2. If we are given only the masses and initial velocities, we are working with 4 unknowns: v1f, v2f, theta 1 and theta 2. But we cannot solve 4 unknowns with 3 equations. Thus, only if we know any one of these 4 quantities, we can solve the 3 equations for the remaining 3 quantities. To summarize, in a two-dimensional collision, after collision, the objects move at an angle to their original trajectory. In an elastic collision, total linear momentum before and after the collision is conserved. Total kinetic energy before the collision is equal to the total kinetic energy after the collision. In our journey of mechanics so far, we performed all our analysis by considering the bodies as point masses. In reality, almost all the bodies we practically encounter are distributed mass systems. While analyzing their motion, we will need to learn and apply some additional and interesting concepts. Stay tuned as we will soon explore the interesting mechanics of such bodies.